Okay, let's talk about DNA replication. I have this fancy photograph. I made it myself. Just kidding. So this is a picture of parent and daughter DNA strands. The outside strands are the parent DNA strands, and the inside ones are the daughter DNA strands as they're being synthesized. So the origin of replication is right here. And we know that because this is where the DNA begins to separate when it's about to replicate. And so it starts opening here, and then it keeps on opening all the way down the line until it's completely unzipped or unglued. And that is made possible by this little guy here called helicase. And this is an enzyme that breaks apart the hydrogen bonds that bond the original parent strand DNA together, or that bonded, and it creates what this is called a replication fork. Basically, this is where the DNA is opening. And so the top strand here, this side is a 3' of the parent DNA, and it goes to 5' over here. And then the bottom, this is 3', and then it goes over on 5' direction. And so DNA polymerase 3, which is what is responsible for synthesizing new DNA, only moves in the 5' to 3' direction, which means because it moves in the opposite direction of the parent strand, or builds in the opposite direction as the parent strand, since this is 3' and this is 5', is going to be synthesizing in 5' to 3', which is A-OK for DNA polymerase 3. So it moves very easily in a single strand all the way over here. As the helicase opens this, it synthesizes and synthesizes. So this over here is DNA polymerase 3, which has synthesized this entire strand of protein very nicely. It started by this little orange guy here, which is called RNA primase. Yeah, it's called primase, and it is made from RNA, and it basically lays the foundation for the DNA polymerase 3 to start making that DNA. And la-di-da, all the way over here. And you can also see these two little guys are called the single-stranded binding proteins, and they basically just bind to, once the parent DNA separates and it has a single strand, it binds to that single strand to basically keep it open so that it doesn't just like reshut, so that it stabilizes the single strand of DNA as the new strand of DNA is being synthesized. However, the bottom here is a trickier situation, a lot more going on, because this is 3' and this is 5', and the DNA polymerase has challenges with that. Yeah. So it started here, and the RNA primase laid the foundation here, and it moved in this direction, but it can't move in that direction. So then it basically has to jump back and start another strand of DNA, or a fragment of this strand of DNA called Okazaki fragment. And then that starts building, and then it jumps back and makes another one. And so all of the little fragments eventually get bound together by what's called DNA ligase, which is like a glue. And that looks like this guy here. And so this glues the Okazaki fragments together so that they are one strand of DNA like this at the end, because any breaks in a strand of DNA would not be good. That wouldn't work. So once the RNA is used for the DNA polymerase 3 to synthesize a new strand of DNA, it needs to go away, because we can't have RNA in DNA That just doesn't work. And so we have this guy here, which is called DNA polymerase 1, which basically removes the RNA and replaces it with the DNA nucleotides. And it replaces it with complementary base pairing, which basically means that there's specific nucleotides that pair with other nucleotides. So there's adenine and thymine and guanine and cytosine. And the adenine, or A, and thymine, or T, A and T always pair together. And then guanine and cytosine, G or C, they always pair together. So if the parent strand of DNA goes, let's say, ATGC, then the new DNA would go TACG. I'm pretty sure I did that right. And basically complementary base pairing. So that's how it's synthesized in a specific code. Yep. And let's see what else. This is the primase right here, which left these little orange sections. But this is the actual primase. These are the single-stranded binding proteins as referenced above to keep that guy open and stabilized as new DNA is synthesized. And gosh, I think that's it. I think that explains it. Hope that's good. I'm going to pause this and go to the second